Lukas Droemer from Nexperia on ESD protection for automotive applications. So welcome, Lukas, and have a good presentation.
All right. Yeah, it's nice to meet you here. Thank you very much for having us. And before I start, I'd like to send some warm greetings from my colleague Andreas, who cannot join in person because his wife is expecting a baby. So that's, of course, the pray one for him. But he wished to join in person. So today we would like to share a bit for the ESD protection considerations. And we saw in the voting that electromagnetic compatibility, EMC, is quite a topic that needs to be addressed when it comes to Ethernet design, and will be even more important when we increase increase the data rates and go to multi-gear with Ethernet. But I don't want to show more on the protection layers we have here, but show a novel approach in simulation that can really save a lot of time, save engineering effort, and could also be a value contribution in the works of standardization. So we had a lot of discussions and presentations yesterday, and also starting today, that we have this transition from the flat wiring harness into the Zona Architecture. And we have also, we heard it from Graham yesterday, we have the people-centric approach. We have a different model of ownership in the car, so that's all shaping the requirements we see here. And what we believe is that at some extent, those different protocols and vehicle networks we have, they will coexist at some point. But definitely Ethernet is and will be the backbone in order to achieve this. So Lars mentioned yesterday for the Max Act the defense on a security level, and when it comes to physical layers, electromagnetic compatibility and ESD can also be seen as defense. And in that sense, we have different compliance tests, and we differentiate here in two groups. So the first one is the environmental testing. So here we have the lifetime test, the mechanical robustness, dust, climate, a test that all have influence on the car itself. But then we also have another group of electrical testing. So and here we have the board process, we have EMC, but especially electrostatic discharge is an issue that needs to be discussed here. And before I will share the approach of the simulation, let's take a step back. So what is ESD exactly? So ESD is the abbreviation for electrostatic discharge, and it's a triboelectric effect that can appear suddenly, and it's a discharge that can happen between persons, device components, cables. So the possibility of this failure mode is very high. And we know the examples. So for here we have a carpet. If we walk on it, we charge ourselves, and if we touch another person, we know the effect of this discharge, but in human beings it's not critical. But when we transfer this to electronic devices, it can really cause this micro-level damage, which we see here on the pictures. So this is really, the ESD is really melting the physical layers, the gate oxide, the metallization layers, the PN junctions of an IC. And this is really a problem because this is causing malfunction, and this damage is irreversible. And if we have electrical overstress, EOS, then if you look on the PCB, we can really see the damage because the package, the mold compound is melted. But when it comes to ESD, we have this micro-level damage which we cannot detect visibly. So this is something we really need to focus on, and this will be a challenge for Ethernet even more. So we just saw the presentation of the shrinking of the feature sizes of ICs, and this is necessary in order to achieve the performance that is needed. And this is a general trend, so not only for automotive or for Ethernet PHYs, but in various market segments. And here's a graph where you can see on the y-axis representing the gate thickness of the PHY, and on the x-axis we have the relative design cost. The gray area is showing the feature size of the PHY, and the little orange box, this is the area on chip we need in order to achieve 2 kilovolt human body model robustness. So this is the typical value we know from the assembly and the manufacturing lines. And what we now see here is that the more we decrease the size of a PHY, we see that this design ratio becomes rather unhealthy. So in order to keep those 2 kilovolt human body robustness, we would need to spend at some gate size more space on chip for the ESD protection than the feature size itself. So in general, ICs become less robust against ESD, and this requires new approaches in order to keep this system level robustness and have a good EMC performance. So with the open lines, so ESD protection itself is not a new concept, and there are various approaches here where we can add discrete components, and silicon-based, varistor-based, and others. And for the, let's say, classic Ethernet before the open lines, it was common to position this ESD device in the schematic between the common mode choke and the PHY. That's what we see on the right-hand side. And this is a little bit tricky because we always have on-chip ESD protection, but we also need discrete external ESD protection. And in this case, the protecting behavior of both components should be matched. So, and this can cause, in some cases, link errors, bit errors, and there's a tricky sourcing situation sometimes. And in this case, we're also not protecting the passive components. So with the open line specification in hundreds and thousand base, it was the first time that in a specification in the TC12, really ESD protection devices were covered. And it makes sense, it makes much more sense to decouple the external protection from the PHY and position it at the connector, because here, in case of ESD discharge, the protection devices work as a current divider, and we have the best protecting behavior. We now have the PHY decoupled, so the matching of the internal protecting behavior and the external is less critical. And with this approach, we are also protecting the common mode termination, the passive components, the common mode choke, and the PHY. So this is the system level view. With the specification, it's not just the position of the ESD device we have here. There are also a lot of other tests that needs to be fulfilled, and we have on the device level some requirements like the trigger voltage of 100 volts because of the DPI test. We have the very harsh requirement of 15 kilovolt discharge with 1,000 discharges. So this is a very harsh requirement which we've never seen before in any other specification. And we have, most important, the ESD discharge current test where we measure the residual current. This is defining the system level robustness. And then we have other tests like the mixed mode scattering parameters to monitor the insertion loss, return loss, and mixed mode. So this is the signal integrity. We have the damage from ESD, so we measure those the signal integrity before and after an ESD event and see, of course, the measurements should match here. And in the end, we have the fourth test, which is the unwanted clamping, and this is also measuring the immunity. So with EMC and with Ethernet, the key takeaway here is that the tests become more and more complex, and it's not just one ESD test you perform and then you're on the safe side, so it's much more that needs to be considered. So mentioning the ESD clamping test, so this is here rather the proof of concept, which is covered in the specifications, and here we have the model. So we use an ESD gun, we measure the residual current at the PHY in order to get an evaluation of the system level robustness. In the specification, the PHY is represented with a 2 ohm resistor. So this is a general value and also worst case scenario. And then we have the human body model JEDEC classes 1 and 2, which give us limit lines for the pass or fail criteria. So this is all covered in the open line specifications, and those tests need to be performed. But with testing, the challenge is sometimes it's trial error, it's time consuming, it costs money, it costs time, sometimes samples are not available from either sides. So that's why we promote a simulation approach. It's not new, but it's not that widely used. And this is SEED, System Efficient ESD Design. And the schematics we see here is actually like under measurements, but we're taking this on a simulation approach. So, and this is really saving a lot of time, saving a lot of cost. It helps to have more design iterations when it comes to application design. And it's also helping in terms of standardization work because we do this in ADS, so we have much faster feedback. So very quickly, just to show how this is working, so the ESD gun itself is represented with an equivalent circuit-based model. The common termination, the decaps, and the IC is represented in a network of lumped elements. And the special flavor really comes in with the dynamic models of the ESD protection device and the common mode choke. So let's go quickly into the different parts. So the basis of the simulation, again, is the ESD discharge. And here we use a 1 kilovolt discharge on a 2 ohm Pellegrini target. And according to the waveform of the IEEE 61000-4-2 standard. And what you see here on the graph is the discharge current over time. And the black line is the measurement. We see this is the waveform from the norm. And the red dotted line is the simulation. So this was also covered in a paper by Young in 2017. So we see here we have a very, very good match between the simulation and the measurement. So this is the basis for the simulation. Then let's move on with the ESD protection. And here we use an approach called TLP, transmission line pulse. And there we take the average values of current over time and voltage over time. And by that, increasing the current and voltage incrementally, we get those averaged points in a range of 70 to 90 nanoseconds. And then replacement in this graph here. So where on the y-axis we have the current and on the x-axis we have the voltage. And this is representing then the real protecting behavior of such device. And also here we see a very good match of the actual measurement and the simulation. The same thing is done for the common mode choke. Here we also use this TLP approach and different voltages. And again, here we have the colored line, so the common mode choke starts to block, it goes into saturation stage, and then the current is clamped. And again, also here, with this model and this design approach, we see a very good match between simulation and measurement. So when we bring all this together and simulate everything, we get the following clamping graph we see on the right-hand side. So when we're measuring the residual current at the phi, and here you see in yellow the class 2 limit line, and again the black line is the measurement we know from the Opalance test, and the red line, dotted line, is the simulation. So SEED is a very nice approach to discuss EMC, to discuss ESD protection in the designs on a physical layer, to have some good discussion and also discuss new ideas. We can also then extend this to a system level. So in this case, on the bottom we have an example of 2 phis, and here in this case the ESD discharge is symmetrical on the capacitive lines here, and also there we see again a good match of measurement and simulation. So that was a simulation approach showing that it really can help and support, but with all the protocols shown in the beginning, we see that in order to keep the good signal integrity, we have the major requirement, meaning the capacitance. So the capacitance, the parasitic capacitance, is really worsening our signal integrity. And if we see the increase of the data rates, we really must go in a very low range of below 1 picofarad. and this can become an issue because as for ICs, we have here the ratio or the dependency of size and capacitance, and this is something that will be tricky. So for the discrete components, silicon-based at least, we see the trend of miniaturization. So at some demos we see how the component density on the PCB is increasing significantly. So we cannot use those large packages and large crystals, the die size. So we need to shrink this while keeping the performance. And here we come to an, let's say, technology and at least an automotive. So from computing and mobile, we have solutions, but in automotive we have those harsh lifetime and quality requirements. And here we are pushing for a new approach called a flip chip land area package. So this is then a substrate-based package where we flip the crystal and eliminate the bond wire. And this is a new approach we're discussing with tier ones in order to have a high performance part that still offers very good signal integrity with the EMC requirements we see from Multigear Ethernet in the future. Coming to an end, ESD requirements are one part, but then we saw some considerations also in the other presentations when it comes to schematic designs, and these are just three examples where we can think when it comes to Multigear a bit how this could be engineered. We can think of a high voltage approach. This is the first one, similar to the Open Lines 100 and 1000 base T specification, so with a high trigger voltage, and this concept would be also ready for Poodle and would really give the best set of performance. But we can also think of a low voltage approach where you either position the ESD protection between the common mode choke and the caps, or also before the capacitors, and this would lower the cost because we don't need such powerful devices. We would have better clamping, so better system protection and better signal integrity. But this is something we are very open to discuss. We have here more ideas, and we will also hear the presentation from Michael and Jamila later today for the cable impact here for EMC. So this is something we're definitely open to discuss. I want to share here different ideas on that topic. So to sum up, we see those mega trends in every area. So it's affecting security, it's affecting the physical layers, TSN and others. For EMC and for ESD, this means that the classic approach of try and error of just doing measurements and just placing some diodes because out of experience, this is not sufficient anymore. And it needs new approaches, and here system efficient ESD design seeds can helping to have more design iterations, to have lower development costs, and to combine this with new requirements we will see in the future with EMC and ESD protection. We are happy to support here your designs and contribute in the next standardization discussions. Thank you very much.
Okay. Thank you, Lukas. I have a question to you. As you're sort of presenting the simulation results and the sort of measurement and aligning the simulation, my question is, who would do this type of simulation? So would you do it in order to develop the right parts, or would also somebody else, is it a tool that somebody else would use?
Yes, so it's running in ADS, so it's something that everyone could use, definitely. At this stage, because there's not a library for models available, it's something that we are doing, definitely. So we have customers that come to us, or car OEMs that come to us and ask for simulation. Mm-hmm. But in the long run, our motivation is definitely to some sort build a library of models, and so that also customers and engineers can perform those measurements, because then simulations, of course, because then we have this trial and error phase. Yeah.
Mm-hmm. Okay, thank you. I have a question from Haysam.
Yes.
Can you guys hear me?
Yes.
Yes.
So if you go back to the slide where you had the 2 ohms for the IC,
Yeah.
did you try to put the actual termination of the IC, the front-end termination that has the capacitance for ESD instead of the 2 ohms as a model?
Yeah, so the parasitic capacitance is added in general. So same for the ESD protection device. So it's not only the clamping behavior, but also the parasitics that is added. And we have measurements done where we try, or where we measured the protecting behavior of the PHY also with this TLP approach. So to have the exact protecting behavior. So that's what we did. It's more a complex approach, definitely. But what we see is that the 2 ohms is an average to the measured PHYs is a good representation. Yeah.
So the 2 ohms will be more of a lumped representation. Is
Yes,
what you're
exactly.
Okay.
But
Right,
if you
thanks.
like, so from Sergey Bub, our contact from Nexperia, who's let's say the head for the seat simulations, we can share some investigations we run here where we measured different PHYs from different vendors and see how they perform in TLP and how this is resulting in the simulation.
Okay, thank you.
Thank you, Asan.
Okay, the next question from Jamila.
Okay, thank you for the presentation. I just have a brief question on one of the slides. I believe it was 46 or 45.
Yes.
It's the next.
This one?
The one with the complete, yeah, but we can also use this one.
Maybe this one?
Yeah, exactly. So I was really interested to have an understanding to what extent the modeling of the transmission line was considered.
Yeah, so that's a very good point. So the trace, you mean the traces, right, on the PCB?
Yeah, because my understanding, please correct me if I'm wrong, you have the different models defined for the different components, but on the other side, they're interconnected, so there has to be some equivalent circuitry for the transmission line at the PCB level that has to be considered.
Yes, that's perfectly right. So we, in the model, we have some standard values, let's say, for the inductance of the traces. So that is covered in the simulation model. And then, of course, you have some dependency where you position, for instance, the ESD protection. So what is the length there on the traces? It's something I can check in, offline with Sergey. What is are the standard values here? But for sure, the inductance of the traces is covered here. So all the parasitics that come in the components, also from the mode termination, the decaps, this is captured in the simulation. So it's really trying to have this system-level coverage. Yeah.
Okay. One last point. It's regarding, it's one of the last slides, regarding the multi-gigabit topic in terms also to the low capacitors issue.
This one here? Yeah.
The next one.
The next one, yeah, okay.
I feel like this is a very tricky topic because it's also interesting to have an understanding how low can we go with the low capacitance and to not affect the signal integrity of the whole transmission. How do you personally see it as an expert in this field?
So in general, the parasitic capacitance we should be as low as possible. So in the field of 2.5, 5 gigabits or 10 gigabit per second, I would see a value way below 0.5 picofarads, so something in the range of 0.3 or 0.2 picofarads. And this is something we're targeting with the, just go back one slide, so this is something we're targeting with this package approach here. Why is that? So we have also comparison, if you take the scattering parameters mentioned before, so there's an evaluation of insertion loss, return loss, and there you see really the impact of different capacitance level, and you see a significant decrease when you go into the range of 1, 2, 3 picofarads. So for multi-gear bits, our view is really to go way below 0.5 picofarads. Yeah.
Okay, thank you. I think I may have additional questions, but
yes, please.
We can freely discuss later as well. I think it's an extended topic. Thank you.
Thank you very much.
Okay. Then there are no more questions. Thank you, Lukas, for
Thank you
your
very much.
presentation. Okay, and I think we're ready for our next coffee break.